Okay, for our next example, I want to, whoops, oh wow, there we go. I want to show that the Taylor series for cosine of x converges to cosine of x for all x. And we did this with the ratio test to find an interval, to find a radius of convergence and an interval of convergence. And we showed that the radius was infinity, so it converged for all x. And that is completely valid. And that's definitely the way we usually want to solve this. But we should be able to apply what we're thinking about here with error bounds to show that this is also true. Specifically, I want to show that as we let n go to infinity, the error goes to 0. Because if it didn't, then that would mean that there wasn't a convergence, right? Like the difference here in my formula, where's my formula? Between this f and p sub n, like that should be going to 0. If p sub n converges to f, then by all logic, these two things should be getting closer and closer together as n increases, making this upper bound 0. That's what should be happening. So we want to show that. And it's not too bad to do. So I want to point out some things first. So the first thing is we're talking about cosine of x, and we want this to be for all x. So the first thing I'm going to do is fix x. And when I say fix x, I mean just treat x like a constant. Like x could be 10, it could be a million, it could be 0.1. It doesn't really matter. We're going to show this works for all x. So just make x arbitrary. It's just some number. We don't care what it is. We're just going to let it be a number. So fix x, I guess I could elaborate to, to be some element of the real numbers. I don't really care what it is. It's just some constant number. And then I'm going to note that f to the n, the nth derivative of x, will always be plus or minus cosine of x or plus or minus sine of x for all n, right? If I keep taking derivatives, I'm just going to keep switching. So regardless of what degree Taylor series I have, this f to the n or f to the n plus 1 will always just be some cosine or sine evaluated, or x evaluated. No, I'm saying it wrong. Some cosine or sine evaluated at our fixed x. And we've done this before when we were first trying to prove that something converged. We can say, thus, f, the absolute value of this, regardless of what n is, this has to be less than or equal to 1, because cosine and sine only go up to 1. So, and we take the absolute value of it, so we can let m equal 1, because no matter where we are in our interval, and no matter what x is, we will always be bounded by this 1. Okay? So notice that if I'm thinking about my steps, I've really just done step like 1 and 2. I considered the derivative. It was pretty straightforward. And then I found m, and we didn't have an interval to think about. We were thinking about any x, but it doesn't matter because cosine and sine are always bounded by a specific x value, or bounded by 1, regardless of the x value. Okay, next, we're going to set up our our error formula. So note that the absolute value of the error of, whoops, I think I want n. Yeah, not 4. We're doing just general n. This, which is equal to the function, which I guess actually we could just go ahead and write it. We know what f of x is. F of x was our original function, cosine of x, minus the Taylor polynomial of x, regardless of what n is, has to be less than or equal to m times, now cosine is centered at, did I say that up here? No. We can treat cosine as being centered at x equals 1. Or 0, I mean. Right, because cosine is symmetric about x equals 0. X equals 0. And we're going to have this goes to the n plus 1, and then this is over n plus 1 factorial. Now we just said that m is equal to 1, so this means that our formula is actually bounded by an x minus 0 is just x. So it's actually bounded by x to the n plus 1 over n plus 1 factorial. So there's our formula. Now, we want to show that the error is going to 0 as n goes to infinity. That's our goal. Because if that's true, then that means that the errors are going away as it increases, and so if the errors go away, it means we converge to the function, right? That's what I said right here. Let's make this a different color. Like, that's what we're trying to get to. So what I want to do is we're going to consider the error of successive, well, we're going to consider the ratio, I'm going to change this a bit, the ratio of error successive terms. In other words, I'm going to think about the limit as n goes to infinity of e sub, a new term divided by the old. Now this should be, the old term should be, the error should be larger for the prior term. The idea is that as n increases, the error is going down. In other words, the ratio between terms should be going to 0. Let's see what this equals. Well, this is going to equal limit as n goes to infinity of, okay, this is going to be, I got to be very careful. So if I plug n plus 1 into our formula up there, I'm actually going to have the absolute value of x to the n plus 2, because it's already plus 1, over n plus 2 factorial. And then I'm going to divide it by what we had before, so x n plus 1 over plus 1 factorial. What does this really equal? It's to infinity of, okay, so let's simplify this. What I really have here is I have x to the n plus 2 over n plus 2 times n plus 1 factorial times the reciprocal n plus 1 factorial over x, absolute of x to the n plus 1. Stop recording. I want, there we go, colors. Okay, so those go away, and the n plus 1 goes away, leaving just 1 left over. And so what I'm left with is the limit as n goes to infinity of the absolute value of x over n plus 2. And you might be looking at this and being like, well, how does that help us? But remember, x is fixed. We said that x is just some random number. We don't really care what it is. We're saying x is any old number. Regardless of what the number is, if we just make x some constant number, at that place, the limit of any number divided by, right, this is really saying some constant number, the absolute value of some constant number divided by infinity, if we throw this limit in here, and that will always go to 0 regardless of what this number is in the numerator, because it's just some constant. I mean, if anything, you could think of it as, you could also think of it as x, which is some constant, times the limit as n goes to infinity of 1 over n plus 2. This right-hand side will go to 0, making the whole thing 0. That's another way to think about it. Either way, it's 0. Thus, we see that the error has to go to 0 as n goes to infinity, because if the ratio of, I want to make sure I say this correctly. Yeah, okay. So if the ratio of errors is getting smaller and smaller, and remember that the errors, we take the absolute value every time. If they get smaller and smaller every time until eventually the ratio is 0, they must be going to 0. They can't go negative because this is a ratio of absolute values, right? So if the ratio of these absolute values is getting smaller and smaller, that means they're getting closer and closer together, and the error is going to 0. So we could technically, we could at the end here say thus the Taylor series for cosine of x converges to cosine of x for all x. That's the main way to wrap it up. But I guess if we want to be elaborate here, so what's happening here? Okay, I think that wraps it up nicely. So the absolute value of the ratio of errors is getting smaller for each new term. So if we imagine continuing this forever, this absolute value of the error has to go to 0 since there's no way for it to go negative, right? If it's getting smaller and smaller and smaller, it only has two options. Either it gets tighter and tighter to 0, or it dips below 0 and goes in the negative infinity direction. But because we are taking the absolute value of things, we prevent that negative infinity from happening, so it has to go to 0. Yeah, that I think is the best way to say that. Let's see what else I want to say now. On the written homework, number number 21, I think, is the one I assigned. It's 21 or number 22. I can't remember which one. But it uses the same idea. It's done the same way. It's done the same way where we set up some limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial, and multiply that times, we'll divide it by the prior term, which is x to the n over n factorial, which ends up basically simplifying to the limit as n goes to infinity of some x over n plus 1. So it uses the same idea. You get to there, and then you have to set up this ratio. But basically the takeaway of this let's see how do I want to say this. That ratio is just a more detailed explanation of the fact that the limit as n goes to infinity of x to the n over n factorial is indeed 0. So like here, for example, where was it? I got to right here. Right here, I have some x to some n over some n factorial, and I want to think about the limit as n goes to infinity. The limit of this is 0. This does go to 0, but that's kind of hard for people to see right away. It makes sense when you think about it, but if you haven't seen this before, you might not be sure. Using this ratio where we set up the ratio between successive terms is just a way of proving this here in the green, or basically this here, that the limit of x to n over n factorial goes to 0. You can do it with this ratio, but if you want to take a shortcut and just use the limit right here, that'd be fine to solve something. The idea is this actually makes perfect sense, so I'm just gonna this is gonna be like a little side note. This makes sense because if we think about this, what does x to the n over n factorial look like for fixed x? I'm going to say that x is equal to some constant c, just to make it easier to see what I mean by fixed. If I have x to the n over n factorial, what does that look like? Well, make sure I have this to the right. Hold on, making sure I don't have a typo or anything here. Right. Okay, so let's say x is equal to some constant. Well, so x to the n is just going to be that constant times itself. You know, n times. And the bottom is going to be n factorial, so n times n minus 1 times n minus 2, times times all the way down to 1. And that might not, if you're not seeing it, so remember, c is fixed. So maybe I'll do a specific example. Let's say once n gets larger than c, then the denominator is going to eat up the numerator. Think about like when n equal even like 2c. Like let's say we're taking a limit as n goes to infinity, so n is so large as twice of c. Well, what I have here now is I have n of these, but then the bottom I have 2c times 2c minus 1 times 2c minus 2 all the way to 1. This is going to be much larger because, like, just even look at these first two terms. The ratio of the first two terms is 1/2. So, and if I keep imagining, like, the bottom is going to have, they're going to be larger for the most part. I don't know a better way to say this. You can throw in random numbers and play around with it, but the idea is we're letting n go to infinity, so the bottom numbers are larger than their respective top ones. Like, see, if c is like 10 and n is equal to 20, well then here again, this one here, again, this is basically pretty close to 1/2 because we have c over 2c minus 1. So this is again pretty close to 1/2. And like this one here, same idea. Again, if n is large enough, this one here is basically 1/2, because if n is large enough that minusing 2 isn't going to make a difference. Yeah. And this is like a really hand-wavy explanation, but I don't know a better way to draw it for you. We can prove it the way I've just shown by taking these ratios, but you can think about it intuitively as n factorial is going to be like, if I had a million factorial is going to be much larger than like 2 to the million. 2 to the million is going to be way smaller than a million times 999,100,000 and 9. No, I really struggle with a million. 2 to the million is going to be less than like a million times 999,999, etc. Yeah. So hopefully that made sense. If it didn't at all and I lost you, just focus on this idea of setting up the ratio of successive terms. Okay. I had another example I wanted to go over. On the homework, so let me talk about a homework problem real quick. And when I say on the homework, so written homework, on the written homework / exam questions, if I want to do a specific example, they're all the written homework I assigned are all from the same like chunk, and I'm basically going to take one of them and make it an exam question. So if you look at the numbers like 1 through 10 on the written homework, I'm going to take one of those and make them an exam question. And I'm going to do one as an example real quick, and then that'll be the end of this. Let's say I want to find the bound in approximating .5 to the 1/3 with a third degree polynomial for f of x is equal to 1 minus x to the 1/3. So we're trying to find the bound, the error bound. So this is basically saying we're looking for the e sub 3 is what this is saying. Find e sub 3 basically. So if we think about a couple things here, it didn't say, oh, and I forgot to mention one other thing about x equals 0. I almost forgot that. It does say that in the problem as well, because that would be really important. Okay, so if we follow the steps I did earlier, the first thing we want to do, and I'm going to try to follow exactly. So I think the first thing I did was say find the derivatives, right? Find the derivatives, find m, set up the error. Yeah. So first thing, let's find the derivatives. In this case, we are interested in finding f to the 4th of x because it's a third degree and we go to the n plus 1. So I'm going to set up this table. F of x is equal to 1 minus x to the 1/3. That means f prime of x is equal to 1/3 times 1 minus x to negative 2/3. That means that f double prime of x is equal to, oh, and I gotta be careful. So the first derivative would be 1/3, but then there's a chain rule because of this negative x in the parentheses, so that's negative. Then this next one, negative 1/3 times negative 2/3 is 2/9. 1 minus x to the negative 5/3. But again, we have a chain rule. That's a negative 2/9. And then we have f triple prime of x. This is going to equal, so negative, so, well, it's technically 10, but then again, chain rule is going to make it negative. So negative 10 over 27, 1 minus x to the negative 8/3. And then finally, f4 is going to equal, so 80, chain rule makes it negative, over 27 times 3 is 81. 1 minus x to the negative 11/3. All right, that's step 1. Then step 2, we need to find m. Now, we are interested in 0.5 to the 1/3. Now, I said the polynomial was centered about x equals 0, but specifically, if I look at this, my f of x function, the way I get 0.5 to the 1/3 is by letting x equal 0.5. If x is equal to 0.5, then I have 1 minus 0.5, which is 0.5 to the 1/3. So our interval is actually 0 to 0.5. This is our interval. And if I graph this function, negative 80 over 81, 1 minus x is negative 1/3. I will let you graph it on your own if you don't believe me or don't understand my drawing, but basically it looks kind of like this. It's a negative decreasing function. This is our f4 of x. And remember, m needs to be greater than or equal to the absolute value of f4 on that interval. And if the absolute value is going to make negatives positive, then that means that the maximum doesn't occur here, but actually occurs, so here's 0 or 0.5. The maximum is going to occur here, because even though it's really negative, when I take the absolute value, that will have a larger magnitude than where I marked in red. So m is going to have to be greater than or equal to this function evaluated at 0.5. All right, and let's see. That is going to be, so that's going to be equal to the absolute value of negative 80 over 81, 0.5, or really, I'm going to do this, 1/2 to negative 11/3. The absolute values drop the negatives, so I have 80 over 81. And 1/2 to the negative 11/3. The negative just flips it over, so this is really 2 to the 11/3. That would be the positive value for m. And I believe, let's check on Wolfram real quick. 80 divided by 81 times 2 to the 11/3 is 12.54. Remember, m just needs to be a number that's nice and better than that. So we will just say, hold on, lost my work. Which this is approximately 12.5. So m, we'll just say, is equal to 13. Because again, it just needs to be a nice number. I'm not going to use decimals for m if I can avoid it. All right, so that's step 2. Step 3 is we set up our equation for E sub n. All right, we set up E of n, or in this case, hold on. In this case, we are specifically talking about E sub 3 of x. I keep forgetting that. We're going to set that up. So the absolute value of the error at 3 of x has to be less than or equal to the function. Now, we want to know the error, and remember, we're trying to find error in approximating 0.5 to the 1/3, remember? And so it's not f of x, right? This isn't some general x. We care specifically about x being equal to 0.5, as I established here when I was talking about it in yellow. And so this is 0.5, because we care about that specific value. And we're going to find the error in that to our polynomial of 3 at 0.5. All right, so there's that. And that needs to be less than or equal to m times, okay, so we were centered at, it said centered at x equals 0, so x minus 0 to the, n plus 1, I keep saying that, n plus 1, which in this case is 4, all over n plus 1 factorial or 4 factorial. That means that this needs to be less than or equal to 13 was what we said m is, x to the 4th over 4 factorial is 24. And we are almost done. We just need to throw in x. So again, the x value in question isn't just any old x, it's specifically 0.5. So I should actually change, so these x's need to actually be 0.5. because that's the specific x we care about. I was going to sub it in later, but really we should just be consistent all the way through. Yeah. And if I throw this into a calculator, let's see what it is. 13 divided by 24 times, I've already forgotten, man. 13 divided by 24 times 0.5 to the 4th. Okay, 0.0334 if I want to round up. And again, we want an upper bound, so we will round up if possible. So we will say that that's equal to 0.0334 because that'll be bigger than anything. And that is our error bound. So this, being able to find this value, I expect you to be able to do this on the test. It's basically like the test question, I mean, it is going to be, there's those problems, like I think they're like 1 through 8 or something. I told you to do like 2, 3, maybe 4 through 6 or something. It's those first ones. They look just like the one I just did here. I'm going to pick one of those at random, and that's going to be the one on the test. I went over this one with the class because this, I think, is the hardest one, so hopefully the other ones are easier. But this is what we need to be able to do. And as always, just remember that we can't always check this. Let's do it in green. Let's say I want to check to make sure my work is right. We should always be able to make that work. Okay, if I check this, the absolute value of 0.5 to the 1/3 minus a Taylor polynomial at 0.5 of cosine of x of degree 3. This is equal to 0.5 to the 1/3 minus the cosine series of this. Hold on, I didn't write down all my scratch work, so give me a second. Okay. 1 minus 0.5 squared over 2. Oh, that would actually be it, because there is no third degree. The third degree polynomial for Taylor series of cosine is, that one has a 0 term. We went over that in class. Yeah, so there's the polynomial for Taylor polynomial for, oh, whoops. No. Hold on. That is for cosine is what I was writing there, which is incorrect. We have a binomial is what we're working with, so I need to use a different formula. Where's my binomial formula? Oh, come on. Where's my binomial formula? Ten, 2, 3. Aha, found it. Okay. The binomial, because this is 1 minus x to the 1/3. Is that what we're working with? Yeah. 1 minus x to the 1/3 is the same as 1 plus negative x to the 1/3. And this is our p-value. So you can always derive the Taylor series, but the idea of this example is you should be able to use some of the formulas we went in class to save yourself time. The Taylor polynomial of degree 3 is going to then be 1 minus 1/3 times 0.5. And this is going to be kind of a long string here. So this is a big parentheses. Okay, 1 minus 1/3 to the 0.5 plus 1/3 times negative 2/3 to the 0.5 squared over 2, and then plus 1/3 times negative 2/3 times negative 5/3 0.5 cubed over 6. What does this equal? Wow, that's ugly. Let's see if I can simplify it. This is equal to 0.5 to the 1/3 minus 1 minus 1/6 minus, okay, so the 2's divide out, and I have minus 0.5 squared over 9, and then, yeah, 1 minus that, minus that. The next one's going to be plus 10 over 27.5 cubed over 6, which is not a ton better, but if I type that all into my calculator, and I'll do it on my phone so I can leave this up, since it is a lot to remember in my head. That typed in right? No, I don't. Crap. 1 minus. Ugh. I might just have to call it and say, trust me, because this is a real pain to type. 0.5 to the. 0.5 to 1/3 minus parentheses 1 minus 1 divided by 6 minus 0.5 to the 2 divided by 9 plus 10 divided by 27 times 0.5 to the third divided by 6. There we go. Oh my goodness. Talk about a nightmare. This mess of awfulness ends up being roughly negative, or nope, absolute value, so the negative goes away. Ends up being roughly 0.01. I'm even round it up. Roughly ends up being about 0.02 if we really round that up. And that is indeed less than 0.0334. Works. Because you should always be able to check it. Wow, that is a nightmare to type in the calculator. All right, this is the last video. I will see you guys Wednesday. And I want to show you that claim I made about how any Taylor polynomial of a polynomial is itself. And then, I don't know, maybe we'll do board work right away. This would be a good board work section. So